So linked list is the other simple data structure that we also need to revisit and watch its operations accordingly. Because in the past, when we did linked lists, we may not have ended up using a class implementation, we might have used a static implementation. But it's important to know how we go about implementing a linked list dynamically, because linked lists they do not have a fixed size. They can increase and decrease in size accordingly. So we need to figure out how do we go about doing these memory allocations, as well as how do we make sure that we also delete these memory allocations as a result when we need to contract all this accordingly, so forth. So that's what we're going to be looking at in this particular lecture, how to go about creating what we refer to as a dynamic linked list. Now, linked lists basically operates on nodes, and the nodes follow some sort of sequence. There are two types of linked lists, which are referred to as a single link and a doubly link list. Now, single link lists basically means that each node points to the next node in the linked list, so there's only one path the sequence of nodes can take. A doubly linked list means that there is bidirectional travel within your linked list. So instead of the data only going in one direction, you can actually go in two directions. So I'm going to draw what this looks like here. So for a single linked list, it comes like if we have a node here, it can only go in one forward direction as a result. But for a doubly linked list, we can have our nodes going in both directions as a result. And this is going to be important for data flow within your linked list. Now, you cannot randomly access anything in a linked list. You must iterate through each one of the nodes in order to find a particular value that you're looking for. What helps is that in a doubly linked list, because you can go forward and backwards through the nodes, this actually is a little bit more advantageous than a single linked list. Because now, instead of, you can actually use particular sorting algorithms here if your structure of the nodes are already sorted. Sorry, you can use particular insertion algorithms if your nodes are already sorted. So the sorting algorithms that we just learned, and we also saw in last week's lecture, can actually be applied to sort the contents of the linked list here from the lowest value node to the highest value node. And then once we have this sorted, we actually use a binary search algorithm here for a doubly linked list to find a particular value within your linked list. And because it's doubly linked, you can go forward or you can go backwards throughout the entire list as a result. In a single linked list, because the direction is only one direction for the data flow, the advantage of this is that you don't need to have two pointers. You have one pointer, so you use less memory overall for the data flow of your entire linked list. Disadvantage is that because you're only going one direction, you can't go back in the list. So once you find something, it needs to be that you start from starting node and you go through each one of these nodes until you find what it is that you're looking for. So the explanations that's going to be provided to you here in this particular lecture is going to be focused on the singly linked list. A doubly linked list just only has one additional pointer that just reverses the directional flow of the linked list, and it's not very hard to implement. So we won't be really discussing doubly linked lists in particular. So for a singly linked list, your nodes here will have some data and then a pointer as its structure. And the pointer in your node is indicative of where it needs to go to the next particular node in the link. Note that the last node will always point to null, indicating the end of your linked list. In your doubly linked list, the nodes here will contain data and two pointers. And in this particular case, the pointers here will be towards your next node and towards your previous node. Now, one thing to note here is that for your start node in your list and your end node to the list, that the values of the pointers in these particular cases are going to be different, because for your start list, your starting node here, this only has this pointer here. There's no pointer pointing to something else. So you can treat this as null. And then for your end value here, for your end value or your end node, we only have this pointer here pointing to our previous node. There's no pointer pointing to your next node. So this can also be treated as null. In some particular cases, and it's also a little bit advantageous, you don't want these pointers here being the same null value. You may wish to assign them to some individual values to know that, okay, this is actually going to be the right-hand side end of the list, or this is going to be the left-hand side end of the list as a result. But that's dependent on design and implementation choices. In most generic cases, you just make sure that these pointers here are just point to null as a result. Now, in creating a single linked list, the nodes here use a struct to define how they're actually going to be laying out their data. So we start with the struct construct in C++, and then we have our data here represented by some data type. In this particular case, we have an integer data type. It can be double, it can be string, it can be character, whatever you wish. But the next data that is going to be in our node structure must be a pointer of that same struct that we created. And this pointer is going to be indicative of which is going to be our next node to follow within our entire link. So we use the struct here to define the structure of our node, but we use a class here for our linked list to define how our nodes are linked together as a result, forming our entire link. Note here that we have two pointers of the node struct, which is going to be head and tail here. And these pointers here are going to be very important later on to indicate the start of our list and our end of our list, and how we go about expanding our lists accordingly as a result. Note that in creating our linked list here by our constructor, which has the same name as the class, once the linked list is empty, the head and tail nodes here, or the node pointers that we see here, are also empty. That's why they get assigned to null as a result. And initializing the linked list, this is the main function for doing this as a result. And in calling the linked list A here, when we create object A of type linked list, the constructor here is automatically called, creating and assigning head and tail to null as a result. So the head and tail node pointers that we just now saw here are important for tracking the first node and the last node in the entire linked list. And we're going to see that when we create our function here to add nodes into the linked list, our head and tail here are going to be affected as a result. So I'm giving you guys the code here for adding a node to the linked list. And we see here that we make use of the new construct, the pointers here, for our node structures in order to create new nodes accordingly in memory. By creating a temporary node constructor and assigning data and the address bit, we can go about reassigning the flow of our linked list depending on how many nodes that we actually do have. So if our head node here was equal to null, meaning that there was no start node, we can say that this temporary node, is going to be our started node for your entire list. So you can put head and tail being the start, because there's only one node in the entire list. If it is not, on the other hand, we need to make sure that we add this node, it goes towards the end of the list. So we update our tail node accordingly to represent. Because this add node function is a method in our linked list class, we call it in our main function using this syntax construct here. In traversing the linked list, remember we need to visit each node in order. So what we end up using is that we end up creating another node pointer to go about traversing the entire linked list and obtaining the contents without modifying the contents of the linked list. Now for a single linked list, when I drew that illustration, remember there's only one direction for the entire data flow of the linked list, so it goes from head to tail. In the doubly linked list, it can actually go from head to tail and tail to head as a result. So all the cases from here on forward will be for single linked lists. So this display function is responsible for traversing the linked list, and like I said, we use a node pointer here. We set that node pointer to the start of the list, and once this node pointer doesn't hit null, being the end node of our list, we are able to retrieve the data at the current node we are at, and we can update our temp node here to point to the next particular node, and then retrieve that data from the next node until we hit a null pointer as a result. In inserting nodes into our linked list, there are three cases that we have to pay attention to. The first case was where we added a node to the end of the list using our add node function. But the other two cases would be where we need to add it at either the beginning of the list or between two existing nodes within the list. So let's see how we go about doing this for each one of them. So if we wish to insert a node at the beginning of our list here, and this node here is being our new node, we create the new node first, and then we need to point this new node here to the head of the existing linked list. And then we need to switch the head of the existing linked list here to point such that it starts at the new node that we created. So this comes back where we update our head and tail nodes accordingly. Right, this insertion, we're all focusing on the head node. This is why we go about doing this in this particular order. So we create the new node first. We set this pointer here for the new node to point to the existing head of the linked list. And for this new node, we switch head here to start at this new node that we created. The code for this actually is very simple. You can see basically it's only 4 lines of code that you need to put in, and this entire method just goes inside the link. And inserting a new node in between two nodes, we won't have to break the linked list and reform the links accordingly as a result. Now, this process only works if the nodes have what we refer to as unique identifiers. And that's going to be a different data field within your node structure itself. In some particular cases, you may want to treat the data field that is already existing in your node structure as the unique identifier. And once we have unique identifiers assigned to each one of these nodes, we can use the identifiers here to search for the nodes that we wish to insert our new node in between as a result. So the steps taken for this is that you need to make your traveler node similar to that of the display function that we saw earlier. And we start at the head of the list, and we check each node to find that unique identifier or data value. If we find that data value, in this particular case, we'll be inserting the new node after this found data value node. So we just then perform the following steps, so is that we create the new node, we assign the data and as such, and then we need to make sure that the pointers here match back accordingly as a result. So the pointer of the new node needs to be set that to the value of the pointer in the traveler. Because remember, the traveler here is going to be at the current node at which we were at. So just to illustrate, what this looks like. Let's call this our traveler. And let's say you had all these nodes here going in. So if the traveler here was at this point, and we have our new node here, call this NN, and it already initializes all our data and so forth. So because the traveler here, I'm just putting an X here, at this point, the traveler needs to make sure that this new node here grabs this pointer that exists from this particular node. And then it needs to make sure that once this new node here goes in here, and it knows its point in here, that the existing node here now points to our new node as a result. So in doing that, that makes sure that the order of the list and the traversal of the list is maintained. Now the code for this is actually given here as well, and it's just basically knowing the sequence of steps to go preserving the order of the list by inserting a new node in between two existing nodes. Similarly, addition of nodes, we also have deletion of nodes from the linked list. And it's just basically just knowing how to go about doing correct order for deleting these nodes safely, and also maintaining the traversal throughout the list such that you don't break the linked list as a result. So if we had A, B, C here, where A links to B and B links to C, and if we had to delete B, we have to make sure that A now points to C, and then once this B node is isolated, and then safely delete B as a result, maintain the order of our linked list. The general code for deleting a node here is given to you guys as here as well. And just pay attention to how the order of our instructions are given regarding how we go about separating the existing links, reforging these links, and then deleting them. Now, in this particular code, there's a problem because this does not consider if we try to delete the node at the head of the link. So, in this particular case, we're going to have to create a different method. And we can see here that the code here for just deleting node at the head of the list is only going to be 4 lines. It's very simple. So, for linked lists, all those functionalities that we saw here is just knowing how to safely insert and delete the nodes, and how to safely add and delete them depending on the positions where they are. And you have to make sure that you always follow the order of operations in order to maintain the integrity of the linked list, such that you don't break it, as well as how to safely delete the nodes once you maintain the integrity of the linked list. And as your homework regarding linked lists, try to figure out how you can merge those two deletion methods for the nodes into one method. Alright, so that brings us to the end of our linked list lecture. Are there any particular questions regarding the content of this lecture? Alright, doesn't seem like we have any questions. So if there are any questions regarding the contents of today's lectures, feel free to leave them down in the comments below or directly email me. Regarding Wednesday's session, we may do like a quick tutorial regarding the operations of each one of these particular functions, just to see how they do operate. If not, we'll do a short review session if as required regarding any particular misconceptions that we may have regarding stacks and queues and the linked lists, or anything that we need to further explain regarding the sorting algorithms as of such. So until Wednesday, take care, be safe, and I will see you guys soon. Later.